So let's skip to IP addressing, and I move to exercise number 3. We have an exercise about subnetting, and more specific about variable length subnet mask. So here we have a network, and the block that is assigned, the block of addresses that is assigned to the whole network is 195.56.78.0/23. Okay, and you can see here representation in binary terms, which always help. The trick for these exercises is always to translate in a binary format the byte that is relevant. So in this case, for instance, you could even leave in decimal 195 and 56, while 78 should be translated in binary form, because the mask is /23, so it means that the network prefix finishes at the first least significant bit of the third byte. Okay, so this is the network, and we have to perform subnetting considering the following requirements. So we have a set of 4 LANs, and for each one we have a number of hosts: 150, 60, 55, 57, and 61. And then we have also a set of point-to-point links. We have to divide the network in subnets, indicating for each of them the address and the net mask, and then assign to the router interfaces addresses compatible with subnets that they are connected to, and then fill in the routing tables of all the routers. So first of all, we can identify the subnets that we want to create on the map of the network. And always remember that each subnet should be connected to other subnets by a router. And when we have in layer 2 connection equipment, switching equipment, like the bridge, we don't have spoken yet about layer 2, but the bridge is like a switch and manages frames at layer 2. So this equipment is not visible at layer 3. So whenever you have a bridge, it is included in an IP network. It doesn't separate the network into different IP nets. Instead, the router always separates the network into different IP nets, because you know that you cannot give put 2 interfaces on the same network. Okay. So we have a first IP net, which is this one, a second IP net here, a third here, then another one here, and then we have 1, 2, 3, 4 IP nets to assign addresses in these point-to-point links. All the network is connected to the rest of the internet by this interface of router 1. And you can notice that the address of this interface is 190.131.99.2, does not belong to the address of the block of the network. Okay, it's external. So we can, for instance, name the networks. this will be subnet A, then this is subnet B, C, and D. Okay. How many hosts we have? These two networks, the layer 2 networks, ETH0 and ETH1, are both on subnet A. So in total we have 210 hosts. Okay. If we want to assign 210 hosts, we need at least 212 addresses, because you know that in each subnet you have always the address, which is the network identifier, and the broadcast address, the direct broadcast address. So we need 212 addresses. In order to have 212 addresses, we basically need 256 addresses. Okay. Because always we need a block that is an integer power of 2. And 2 to the 7th will be not enough, because it's 128, which is less than 212. In this case, we need we have 55 hosts, so we need 57 address. So we can stay with a block of 64. Okay. And the same in this case when we have 59. And also the same in the last case. Remember always to count the two addresses that are forbidden. Moreover, also remember to count that for each subnet you need to save one address for the router interface, in case you have only one router. In case you have more routers, multiple addresses, depending on how many routers you have. So actually here we should increase by 1 all this count, because these networks, all these subnets A, B, C, and D have just one router. So here we should be actually 58. This should be 60. This should be 64. But in any case, you see that 64 is always enough. Okay. Then we have the point-to-point links. For the point-to-point links, we know that we need two addresses. We need to assign two interfaces. So it's like having two hosts, but actually are two router interfaces. So we need 4 addresses. Okay. So now that we have cleared this, we can start splitting the space, the network space, in order to create the subnets. And we will have a first split that creates a subnet A, and then a further split to create subnet B, C, and D, and then another one to create the point-to-point links. So now we know that we start from a /23 space, okay, which is the overall network. In order to create subnet A, okay, we need a /24 because here we have 8, the number of bits for the host ID is 8, so 32 minus 8 is equal to 24. Okay. Since we need 8 bits for the host ID, the remaining part, which is 24, is the length of the subnet mask. Since we are increasing the net mask by 1 bit, it means that we are splitting the network into 2 subnets. Each time you increase the number of bits, at the same time you are increasing the number of subnets. The number of subnets that you are creating is equal to 2 to the number of bits of the subnet ID, which is the extension of the net mask. So we have created another block, and we have to divide the other block again. And what happens if we divide the other block by extending the net mask by 2 bits? We create 4 blocks. Okay, that would be the /26. Four blocks are enough because we need to create 3 subnets of equal size, and each one must be 64. Okay. (64) is 2 to the 6. (32 minus 6 is equal to 26. Okay. So we are on the right way, both as a number of subnets and also as the size of the subnets that we are creating. Then there is this remaining block, and we can split it into blocks. Here we can do basically different solutions. One is to split it in with another step of subnetting and then a further step of subnetting. Otherwise, we can also decide to go to /30. Okay. If we go to /30, we create subnets that are useful for that are correct, that are matching the requirements of the point-to-point links. We have just 4 point-to-point links. One, two, three, 4. However, here we have created how many subnets? How many subnets we have? We have increased by 4 bits. Okay. We have increased the network prefix by 4 bits. So the number of subnets that we have created is 2 to the 4. Block number 1, and here we have block number 16. Okay. All the blocks beyond block number 4 are left for a future assignment. Okay. So this is the subnetting scheme, which is complying all our requirements. Now we have to define the addresses of each subnets. Okay. The addresses of each subnet. So we have, let me increase the space. So subnet A, since it's the first one, it will start at the beginning of the block, of the entire block of the network. Okay, so the address will be exactly the same as the block of the network. But the block of the network is a /23. Here we have a /24. Okay. We can also add here the broadcast address. In this case, it's very simple. It's 195.56.78.255. So here we have the first the network prefix, which has all the bits of the host ID set to 0, broadcast address, all the bits of the host ID set to 1. Then there is subnet B. So subnet B starts, subnet A occupies all the block from that is 256 address block, okay, from 0 to 255. So subnet B must start one address above, which is, so we are entering the space of the 79, okay, as address of the third, as decimal value of the third byte. If you remember, in we can write it also in binary notations. In binary notation, 78 is 0, 1, 0, 0, 1, 1, 1, 0. 79 is 0, 1, 0, 0, 1, 1, 1, 1. Okay, and this is allowed. We are still in the block of the overall network, because the original address of the overall network was a /23, so it did not include the last bit. So the last bit can be either 0 or 1. That would be 0, but we are in a /26. Okay. So the broadcast address, what would be? we are in a slash 26, so it means that we have a block of 64 addresses. Okay, the broadcast address is always the last one of this block, and these 64 addresses goes from 0 in the last byte to 63 in the last byte. So you immediately can write the address. Okay. Then we have C. This is the same. And here, without doing any transformation into the binary form, we can immediately write 64, because we know that the previous block arrived to byte number to address number 63. Okay. If we want the broadcast address, we have to add again 64 to this. It's 128, but we have to take the last one, so 127. Okay. D starts with 128. It will finish with 128 plus 64 minus 1, okay, which is 192. Sorry, 191. Okay. Then we have the point-to-point. So we know that the first point-to-point starts when the previous block is finished, so at 192, and it is a slash 30. Okay, so it means a block of 4 addresses. We can immediately write the broadcast address 192 plus 3. Okay. Point-to-point 2, 196, just a second. And here we will have 199. Point-to-point 3 will be 200. Point-to-point 4, 204. Okay. So this is a full list of the subnets, and now we can start assigning addresses to all the interfaces. Okay, and I have to draw how to do it fast. I have to draw the network again. So here we have internet. Here we have the first router that is external. Then we have R1. These interfaces were already given, so we don't have to assign them. Then, here we have R2, and this is the first subnet. Okay. This is 195.56.78.0/24. This is .79/26. Sorry. .79.0/26. This is .79.64/26, 79.128/26. Okay. Then we have the point-to-point links. For instance, this is the .79.192.30. This is the .196.30, .230, and 204. Okay. So here you have to assign, for instance, if we take router number 2, we have to assign to one interface an IP address which is in the range of point-to-point 1 network, and for instance it would be .193, okay? Quindi, so it would be this address. Okay, and remember that you have also to specify the net mask when you are assigning an interface, when you are defining an interface, which is not actually part of the interface IP address, because that is a 32-bit IP address, but it is related to the network that interface belongs. Okay? And here we have to choose another value inside the network, the subnet A block. It's a common practice to assign to the router, to the gateway interface, the last possible address in the block that can be assigned to an interface. So in this case it would be 195.56.78.254/24. Okay. On this side here, let's say that we take a router 1, we will assign the other interface, the other address, so 195.56.79.194/30. Okay. And then you can continue to assign all the other addresses. I don't write everything here because it takes time, but if you have understood the first one, then you know everything. So now we can write instead the routing tables of each router. Okay, let's take for instance router number 2. Okay, here we have a single interface of this router that is leading to the rest of the world, which is the interface towards the router number 1. Okay. Router number 2 is the default gateway for this network here, and all the packets that are going from that network to the rest of the world will go to the same interface. So in this case, the routing table is very simple because we just need the default entry. So in the routing table of router 2, we will write the network column, the net mask, and the next hop. The default entry is this one, if you remember. Next hop will be the interface of router 1, because it's the one that is connected here. So we have to write 195.56.79.194. Okay. Do we need to specify a net mask also in the next hop? No, because this is the address that will be written on IP packets that are going towards router 1. Okay. Actually, here this will be translated into the output interface, that is the physical interface, usually. Say ATH0, where ATH0 is this output interface. Actually, I said a wrong thing. This is not even the address that you write in the IP packets, because in the IP packets there is always the final address. This is the address that is converted into the physical interface when the router is doing the forwarding. Okay. All the routing tables of R3, R4, and R5 are very similar, so I don't write them explicitly. They will always only contain the default entry, okay? Because each of these networks have a single output exit, let's say. The routing table of R1 is more complex. And here in R1 we have to use the specific, we have to apply the distinction between the different subnets. Okay. So since we have already written here all the addresses of the subnets, I just have to report them and associate each address with the correct next hop address. Unfortunately, you cannot see everything, but So here we will have, for instance, 195.56.78.0 net mask 255.255. Next scope is okay. Then there is 79.0, and this will be 255, 255, 255, and so on, 192. I don't write the addresses of the next stops because otherwise it takes too much time. Here we will have the 71.9.64. The net mask is the same. 79.128. The net mask is the same. Okay. Finally, also in this case, we have to add the default and in this case, this router, each time it receives something that is not going to any of the subnets, it means that it has to go outside the network, and therefore it is sent to the next stop, as a next stop, to the address that was 190. Okay. So this is the routing table of router number 1. Let's say that instead of having this topology, we have, let me put it in red, that this link is not existing, and R3 is connected to R2. Okay. So in this case, we could simplify this routing table by adopting the supernetting procedure, because here we have that the first entry is a 78. Okay. So is 0, 1, 0, 0, 1, 1, 1, 0. The second entry is a 79. Okay. So in this case, you see that they have in common up to the last, the second bit. And in this case, when there is this connection between R2 and R3, when R1 receives a packet that is when it receives a packet that is going to this network, to network subnetwork A, or it is going to subnetwork B, in any case, the next stop is always R2. Okay. So since we have the next stop that is R2 and the two blocks that are adjacent, we can compress these two and different entries using the single entry 78.0/23, okay, which is actually the original address of the whole network. But since we are doing longest prefix matching, automatically when you have something that is not directed to those first two networks, but to these other two that are more specific, it will be sent to the appropriate output. Okay. You can do by yourself the other exercises. Exercise 4 is very simple, and also exercise 1. So I wanted instead to go through